I'm like...
Hello, everybody. We are Group 3 working on the optimization of a truss project. I'm Oliver Doban.
I'm Grace Kelly.
So, bridge optimization is an essential part of improving the infrastructure within a country. Given a limited amount of resources, however, it is important to reduce the amount of building materials used to build bridges without sacrificing structural integrity. This project explores minimizing the total amount of material used in the construction of a bridge truss while satisfying yield and buckling constraints. Our team analyzed a truss with the geometry shown. It is assumed that the truss is symmetrical, and given that the truss is designed to support a flat road, it is also assumed that beams 6 and 7 are oriented horizontally. The truss is modeled as being made from A36 steel with a modulus of elasticity of 200 gigapascals and a yield stress of 250 megapascals. The truss is designed to support a loading of 100 kilonewtons per meter, which is roughly equivalent to 4 fully loaded semi-trucks sitting on a bridge supported by 2 trusses, given a safety factor of 2. There are 6 design variables that can be used to describe the radius of each truss member, and dozens more that could be used to describe truss geometry, such as node positions and lengths of truss members. With our simplifying assumptions, however, the full geometry of the truss is boiled down to 6 design variables. 4 variables are needed to fully describe the radius of each member by our symmetry assumptions, and the length of all truss members is fully described only by using the length of member 1 and the overall height of the truss.
The objective function to be minimized is the sum of the volume of each member supporting the structure. The buckling constraint is included, and for each beam, this value should be less than the value that causes the beam to buckle and fail. As for the yielding constraint, each beam's value should be less than 250 megapascals to ensure safety and stability. The objective formula, buckling constraints, and yielding constraints can be expressed in terms of the 6 parameters mentioned earlier. Since the goal of this optimization project is to minimize the total volume of the truss, the volume of all beams are calculated by using the geometry of the truss depicted in the figures earlier and summed in the objective formula. Finally, in order for the bridge to be stable, all 7 beams must fulfill a certain buckling or yielding constraint. Given the yield and buckling constraints, this problem is formulated as a well-posed, constrained optimization problem. The F-min-con function is used to optimize the problem with the default interior point algorithm used. This algorithm was chosen because it can handle large, sparse problems as well as small, dense problems and satisfies bounds at all iterations.
The optimal values found to minimize the volume of the bridge while keeping it safe are as follows on the table shown. It is important to note that beams 2 and 5 will be the same at 0.1229 meters, and beams 3 and 4 will be the same at 0.049 meters, in addition to beams 6 and 7 having the same radius as 0.0502 meters. The volume of A36 steel, that is the optimal value, is 2.0439 meters squared. These values make sense in the real world and show that the problem was well defined. The problem was solved both with and without numerical conditioning. Although the results were similar, it is interesting to note the effect they had on the yield stresses, especially in beams 1 and 2. In conclusion, based on the results of the project, buckling constraints are active for beams 1, 2, and 5, and yielding constraints are active for beams 3, 4, 6, and 7. Some of the lessons we learned in the process of finding a solution was simplifying assumptions about the design early in the process, how to turn physical requirements into mathematical constraints, how to deal with trade-offs, for example, the strength and mass of the structure and its economic impact, MATLAB implementation, for example, how to use F-min-con and incorporate constraints, and finally, the importance of simulation and testing to the success of any engineering project. Thank you for viewing. We hope you enjoyed it.